Imagine an invisible dance, a choreography so precise and intricate that it underpins the very nature of matter itself. This dance isn't performed by dancers but by phonons, quantum entities that do not submit to the classical laws we are familiar with. Phonons, these mysterious quasi-particles, represent quantized sound or vibrational waves within a solid, moving in symphony as the atoms in a crystal lattice vibrate. But recent discoveries have begun to uncover layers of complexity and surprising behaviors in these phonons, leading us to rethink their potential in technology and theoretical physics. This essay explores the enigmatic world of phonons, delving into their unexpected behaviors and the revolutionary applications they might offer us in the near and distant future. The concept of phonons emerged in the early 20th century as scientists began to understand more about the nature of heat and sound in solids. The term phonon itself, deriving from the Greek word for sound, phone, was coined to categorize these carriers of vibrational energy. Throughout the decades, experiments and theoretical advancements have shaped our current understanding of phonons. Notable theories like the Debye model and the development of quantum mechanics have been particularly influential, providing a framework to describe how phonons behave and interact within different materials. This historical context is crucial, as it not only highlights the evolution of phonon research, but also sets the foundation for appreciating the recent groundbreaking discoveries and their implications. Recent research has unveiled that phonons can exhibit behaviors far beyond what classical theories predicted. For example, in non-equilibrium processes, phonons have been seen playing a role that contradicts their traditional passive nature in thermal conductivity. Studies have also shown phonons interacting in unexpected ways with other quasi-particles like magnons and excitons. These interactions could potentially lead to new ways of manipulating material properties for electronic applications, signaling a shift in how we understand and utilize these quantum entities. By examining these surprising observations, this section underscores the dynamic and still unfolding nature of phonon research, suggesting that much about these quasi-particles remains to be discovered and understood. Phonons are not just theoretical curiosities, they have practical applications that impact our daily lives and the technologies of the future. In the realm of electronics, managing heat is a critical challenge, and phonons play a key role in thermal conductivity, making them integral to designing more efficient devices. Moreover, the field of thermoelectrics, which involves converting waste heat into electrical energy, relies heavily on understanding and manipulating phonon behavior. This can lead to more sustainable energy solutions, and is just one example of how phonons could revolutionize technology. This part of the essay explores various technological fronts where phonons are already making an impact and where they promise to bring about transformative changes in the future. The frontier of phonon research is continuously expanding, with areas like topological phononics and phonon lasing emerging as exciting new fields. These advanced topics not only deepen our understanding of phonons but also open up possibilities for developing materials with novel properties that could revolutionize technology. Speculating on the future, it's conceivable that our growing grasp of phononic behaviors could lead to breakthroughs in areas as diverse as quantum computing and material science. This section explores these cutting-edge research areas and their potential to shape future technological landscapes. By delving into these advanced topics, we begin to see just how vast the implications of phonon research are, spanning multiple disciplines and potentially altering the technological and theoretical frameworks we operate within. Superconductivity remains one of the most intriguing phenomena in physics, where materials can conduct electricity without resistance. Phonons play a crucial role in this through the BCS theory, which posits that phonon-mediated interactions between electrons are essential for superconducting behavior. Recent studies in unconventional superconductors suggest that phonons might interact in ways that are not yet fully understood, hinting at new realms of physics to explore. This section discusses how phonons are integral to both traditional and novel superconducting materials, offering insights into their complex behaviors and critical roles. Understanding the interplay between phonons and superconductivity not only enhances our knowledge of both fields but also guides future research in material science and quantum mechanics. In the realm of nonlinear phononics, phonons do not behave as we might expect under classical conditions. When driven under specific circumstances such as high amplitudes or within certain materials, phonons can exhibit nonlinear dynamics like the generation of second harmonic waves or the formation of solitons. These nonlinear interactions provide a richer understanding of phonon dynamics and open up new possibilities for materials engineering and device fabrication. This part examines the complexities and implications of nonlinear phononic behaviors, highlighting their potential in scientific and technological advancements. Exploring nonlinear dynamics not only broadens our understanding of phonons but also exemplifies the diverse and impactful ways in which these quasi-particles influence material properties and technological developments. The advent of two-dimensional materials like graphene has introduced new arenas for phonon research. In these materials, phonons behave differently due to the reduced dimensionality, leading to phenomena like negative thermal expansion and anisotropic heat conduction. Studying phonons in such materials not only deepens our understanding of basic phononic principles, but also enhances our ability to engineer novel material properties for advanced applications. This section delves into the unique phononic effects observed in two-dimensional materials and discusses their implications for future technologies. By examining phonons in this context, we gain insights into how reduced dimensionality alters phononic behavior, opening up new possibilities for material design and technological innovation. Understanding phonon transport can significantly impact the development of materials aimed at enhancing environmental sustainability. For instance, better thermal insulation materials designed through phonon manipulation could lead to more energy-efficient buildings. Moreover, phonons play a critical role in thermoelectric materials, which convert waste heat into electrical energy. Enhancing these materials' efficiency could lead to more sustainable energy solutions. This section highlights how phonon research contributes to environmental sustainability through advancements in material science. The environmental implications of phonon research exemplify the broader impacts of this field, extending beyond pure science and into crucial areas like energy efficiency and sustainability. Theoretical studies suggest that phonons could have applications far beyond Earth, linking them to cosmic phenomena. For instance, phononic interactions might simulate conditions of the early universe in laboratory settings, providing insights into cosmological events and even dark matter research. This section explores the intriguing connections between phonons and cosmology, discussing how studies on Earth could impact our understanding of the universe. By linking phonons to such grand scales, we see the potential of phononic research to contribute to fundamental questions in physics and cosmology. Exploring the cosmic dimensions of phonons not only broadens their scientific relevance but also underscores the universal nature of these quasi-particles. Studying phonons requires sophisticated experimental techniques due to their quantum and non-visible nature. Techniques like neutron scattering, pump probe spectroscopy, and Brillouin light scattering have been pivotal in advancing our understanding of phonon dynamics. This section provides an overview of these experimental methods, discussing how they have evolved over time and what they have revealed about phonon behavior. By understanding these techniques, we gain insights into the experimental landscape of phonon research and its capabilities. The evolution of experimental techniques not only enhances our understanding of phonons but also drives forward the entire field of material science, opening new avenues for exploration and discovery. Phonon research is not just for scientists and engineers, it has educational implications as well. Integrating phonon concepts into educational curricula can inspire future generations of physicists and material scientists, fostering a deeper interest in this fundamental area of study. This section provides resources for further learning, such as key texts, online courses, and seminal papers, making phonon research accessible to students and educators alike. By discussing the importance of education in this field, we emphasize the role of knowledge dissemination in advancing science and technology. The educational aspect of phonon research highlights the need for knowledge sharing and curriculum development to nurture the next wave of scientists and engineers equipped to tackle future challenges. The exploration of phonons reveals a rich tapestry of scientific inquiry and technological potential. From their fundamental role in understanding material properties to their surprising behaviors and applications in technology and cosmology, phonons represent a fascinating area of physics with broad implications. This essay has traversed various aspects of phonon research, shedding light on both established and emerging areas of study. As we continue to uncover the mysteries of phonons, their significance in science and technology is only expected to grow, promising new discoveries and innovations in the years to come. In conclusion, phonons are not merely particles of sound and heat. They are keys to unlocking new realms of understanding and technological advancement, making them central to future scientific and engineering endeavors. Academic journals and papers on phonon research, historical texts on the development of theories related to phonons, recent publications on advanced topics like topological phononics and phonon lasing, educational resources for deepening understanding of phonons and their applications. This essay has outlined the multifaceted nature of phonons, from their basic definitions to their implications in various scientific and technological domains, providing a comprehensive overview of a complex and rapidly evolving field.